All right, so another neat method and powerful method for adding water across a double bond is hydroboration-oxidation. So we have another special thing we can do with this, and that is we can add this in the anti-Markovnikov. Now we can add water in the anti-Markovnikov position, right? So in the Markovnikov position, we expect the hydroxyl to go here, right? And that was what we would do if we did oxymercuration, demercuration, or acid catalyzed hydration. But we want instead to put it on the outside sometimes, right? Depending on what we're trying to make. If we're trying to make something different, then we need a way to get it to the less substituted carbon. And this is the method for it, hydroboration-oxidation. Now, this is a two-reaction sequence. Let me point that out. It's two-step sequence. This is not aqueous. This is aqueous, and so water will kill that. You can't put this all in one. You can't put this all in one bucket. Okay, so let's talk about how this happens. So it is. It's not just anti-Markovnikov. It's also stereoselective. That is, it goes in the syn fashion. So in other words, if the hydroxide comes on the front side of this double bond, so is the hydrogen. If it goes on the back side, so is the hydrogen. And since in this case we have an asymmetric double bond, so we're going to get enantiomers here, and it's going to be racemic, right? It's going to be 50-50, unless we have some other feature which would make this not possible. Some other feature that would make it really, some other really complicator. But in general, these are going to make enantiomers, and they're going to be 50-50. The anti-addition is not observed. If you had another hydrogen here, it wouldn't matter, right? But if it's tertiary, then it will matter. So let's talk about what the THF is doing. So first of all, borane has a similar structure to a carbocation, right? Can you see you've got this unhybridized p orbital here? It looks very much like a carbocation. 3 electron groups with an unhybridized p orbital. The carbocation, of course, has got a charge on it, but otherwise it's very much the same. BH3 is one of the 2 or 3 octet exceptions that you learned about in general chemistry. So this is a weird thing, and it turns out we can use this weirdness to our advantage now. So borane, if it's just by itself, has a tendency to dimerize. And the dimerization looks like this. You've got an unhybridized p orbital here, unhybridized p orbital here. And these electrons, if these guys get close to each other, these electrons say, hey, I'd like to go into that unhybridized p orbital. These ones go, I'd like to go in that unhybridized p orbital. And they switch, right? Intermolecular resonance. That's something you won't hear out of my mouth very often. Intermolecular resonance. Since it's intermolecular resonance, we end up with some dimer that looks like this. Okay? So, in order to stabilize borane by itself, so that we can react it with a double bond, we stabilize it with ether, this tetrahydrofuran, okay, this THF. This ether goes, you've got these lone pair of electrons here, it goes into that unhybridized p orbital, and you get this complex, okay? And this complex is why you have to put the dot. This is a complex, which is a reactive complex that the alkene can work with. Okay, so let's look at it now. You have an alkene, right? And suppose you've got, again, this is really the THF stabilized thing here, okay? So this lone pair of electrons says, hey, boom, right? That's an unhybridized p orbital there. Well, if that's the case, then these electrons say, hey, I can go over there and associate with that carbon. And so we get this transition state. That's what that's about. All right, now it turns out that after that's done, this is ready to do it again with another one. So first of all, that's the first one. And then then it goes again and another time until we get a trialkyl borane, right? And that is an intermediate. The trialkyl borane is here. And this just shows why it's doing it again. I don't want to show that again. Yeah, that just shows why it's doing it again. This another figure which is from your textbook, which shows why, another reason why the borane is going to go on the less substituted, because it's too crowded over here, right? So it's less crowded if it's over on the less substituted, sorry, where's my vocabulary? The less substituted carbon. How could that be a difficult word for me to remember? All right, so here is the oxidation now. This is a mechanism which I will not test you on. I will not test you on this mechanism. It's a great one. I think, you know, I have tested students on it before, but it would add value to your course, but we're just not going to do it. So let me just move on. I'm not going to walk you through it. We'll take time for other things later. But I will say this: if you're not in my class, if you're watching this video from someone else's class or from another place altogether, not even at my school, then it's a great method, and I encourage you to take a pencil and walk your way through it until everything makes sense. It's mostly going to be steps that you recognize from other mechanisms. Okay, so we already appreciated that hydroboration is stereospecific and only syn addition occurs. All right, that means that the hydroxide and the hydrogen both go either on the top or the bottom of this, right? We already said that before. And if one chiral center is formed, a pair of enantiomers is formed by addition to either side. And then finally, I guess I just said that if two chirality centers are formed, again, a pair of enantiomers are formed. All right, I hope this is helpful. Good luck to you. Go practice it.